Hi everyone, my name is Jim Kurose. I'm a professor at the University of Massachusetts in Amherst, and I'm currently on sabbatical at the Sorbonne University in Paris, France. And I want to welcome everybody to MedComNet 2020, and I also want to thank the organizers for an opportunity to present a keynote talk at this conference. If I have one regret, it's only that we're not able to be there together in the beautiful town of Verona by the side of the lake, to be at this conference together and to chat and have that give and take that's so important at a conference. Now I understand that Verona is the birthplace of Mario Jurla, and as many of you know, Mario played an absolutely critical role in the founding, continued operation of MedComNet and MedHawkNet. Now many people around the world know Mario on the basis of his research, but I know that many of us here today remember Mario as a colleague, as a mentor, as a friend, and as an all-around wonderful human being. So I really am honored to be able to give a presentation at a conference in Mario's hometown, and I just wish we could all be there to swap Mario stories over dinner, or more likely to be doing it for a morning run on the beach or a morning swim on the beach with Super Mario. Well, like many of you, this is the first time I've recorded a talk for remote asynchronous delivery, so we'll see how it goes. Most of the time I'm going to be over in a box over here on the right-hand side, but I understand that we're going to have a live discussion later this week, and I'm really looking forward to that. Well, here's what I'd like to talk about. After a short introduction, we'll get into the meat of the talk, to talk about changing network abstractions. Now that may seem a little bit vague to you, but I've found it really useful every now and then to sort of step back, to take a big picture view of what's happening within our field. And so phrases like research moving up the protocol stack or research moving to the edges of the network have been useful sort of macro level roadmaps for me. Now, of course, there's interesting research going on really throughout the protocol stack at all parts of the network, but these macro trends have sometimes been useful for me, again, to get this sort of big picture macro roadmap view of where some parts of research are heading. And the abstractions that I want to follow are from circuits to packets to flows to content and finally to systems. Then we'll wrap up with a quick discussion of teaching and where that might be heading, something very near and dear to my heart, and then wrap up with some final reflections. Well, this picture here is from the movie All the President's Men, when the investigative journalists wanting to get to the bottom of Watergate are told by an informant to follow the money. So here, we're going to follow the abstractions. And to follow the abstractions, to follow the evolution of these principal networking abstractions over time, we're going to need a timeline. So here's the timeline that I'd like to use. I'm sure everybody here is familiar with these landmarks. So let's start in 1961 when Len Kleinrock publishes a paper called Information Flows that later appears in the RLE Quarterly. By 1969, the ARPANET has 4 nodes, and in 1974, Vince Cerf and Bob Kahn published their paper and coined the phrase internetworking. In 1988, there are 100,000 hosts connected to the internet. Van Jacobson publishes his seminal paper on TCP congestion control, and in the same conference, Dave Clark publishes a paper on the DARPA Internet Protocol Suite. In 1998, Akamai is founded, and in 2008, we see the rise of software-defined networking and the beginning of massive data centers. In 2014, 4G LTE is widely deployed, and there are now more mobile users connected to the internet than there are fixed hosts, and in 2018, there are 3.9 billion users connected to the internet. Of course, all of this got started way back in 1909 with the beginning of circuit switch networking and the telephony network. And now let's consider some of the principal networking abstractions, beginning with circuit switching back in 1909 and continuing on through today with TDMA and FDMA and 4G. Packets have served as a principal data abstraction for a long period of time for data networks. Starting in the 1970s, but really ramping up in the 1980s and into the 1990s, the notion of a flow became a very important abstraction. The notion of a connection between two endpoints, even though the underlying network transport service is datagram, connectionless, best effort oriented. Around 2000, we see the rise of content-oriented networking, content delivery networks, and later information-centric networking. And with the rise of software-defined networking in both wired internets and also in 4G, 5G systems, we see the rise of the network as a system. The notions of network management, configuration management, manageability, and quality of experience. So these are the principal networking abstractions that I want to talk about, and let's look at each of these in a little bit more detail now. With circuit switch networks, calls arrive to the network, request resources, and either receive the required set of resources or are blocked. The unit of work, the abstraction, is this call. In this example here, each link has two trunks, and arriving calls are allocated a concatenation of trunks to connect the call end-to-end and hold those trunks for the duration of the call. If a call arrives and there are no free trunks, as in the case of this uppermost call arrival here, the call is blocked and holds no resources. The emphasis here is on simultaneous resource possession by calls, and the performance metric of interest is the call blocking probability. And the classic works here are Erlang's blocking formula from more than 100 years ago and Frank Kelly's work on blocking networks in the mid-1980s. With packet switching, the packet is obviously the unit of abstraction. Packet loss and packet delay are the principal performance metrics of interest. Since we all know about packet switching intimately well, I'm not going to say anything more about packets as an abstraction, except that packets are a very small unit of abstraction. With content-oriented networks, or what has become known as information-centric networking, the level of abstraction is raised to a higher level. The unit of abstraction are pieces of content and requests for that content. In some forms of ICN, what we might call network-centric ICN, content is cached within the network and requests are routed to the nearest copy of a piece of content. And content replacement in network caches is also an important issue, as we see here in this animation. So we see here in these three cases that the unit of abstraction changes from circuit to packet to content, and the research challenges change accordingly as well. Now I reference a paper here that was part of a birthday celebration issue of a journal for Len Kleinrock's recent birthday that talks about this evolution from circuits to packets to content. And in that paper, actually, there's a couple of important things that I left out. So I want to talk to you about some additions I'd like to make to that. And the first of these additions would be to add content distribution networks, CDNs, to the picture here. CDNs have been around almost a decade longer than network-based ICN. And rather than replicate content in the network, they replicate content at the application layer, at the network edge, and direct requests to the nearest or maybe least congested content as shown in these animations here. But the unit of abstraction again is content. I do think that the comparison of CDNs versus in-network ICN tells a pretty compelling story of implementing new higher level abstractions at the network edge in the application layer rather than deeply inside the network itself. Akamai, for example, has replicated content locations in more than 1,700 networks. And the second addition that I'd make on that paper that talks about the evolution from circuits to packets to content is to include the notion of flow as a very important abstraction. Well, let's dive a little bit deeper into this abstraction of a flow. And in the internet world, the notion of a flow really first shows up around 1988. There's a paper in 1988 SIGCOMM by Dave Clark looking retrospectively at the lessons learned from the DARPA Internet Protocol Suite, but also looking forward into the future. And he introduces the notion of flow in this paper. Let me read to you what he wrote there. This suggests that there may be a better building block than the datagram for the next generation of architecture. The general characteristic of this building block is that it would identify a sequence of packets traveling from the source to the destination without assuming any particular type of service with that sequence. I've used the word flow to characterize this building block. Well, so there you have it. The notion of a flow, a binding between a source and destination to a sequence of packets showing up as an important internet abstraction. It's interesting to note that IPv6, which came about half a dozen years later, also had a very strong notion of flow, even so strong as to have a flow ID showing up in the IPv6 packet header, even though the notion of what exactly a flow is not really well defined there. It's also interesting that in 1988, when Dave is writing about the notion of a flow, next generation internet architecture, it's the same conference where Van Jacobson publishes his TCP congestion control paper with, again, this very strong notion of now controlling the flow of packets between a source and a destination according to additive increase, multiplicative decrease. But of course, the notion of a flow wasn't completely new in the broader networking world. In the 1970s, I'd really flag two really important pieces of work that identified this notion of a flow and controlling flows. And actually, the first was a paper on the flow deviation method written by Luigi Fratta, Mario Gerla, and Len Kleinrock. And the second was a minimum delay routing algorithm by Bob Gallagher, which routed flows in a decentralized way using gradient information to deviate flows at individual routers. And both of those had a very strong notion of source to destination pairs and source to destination paths for the flow associated with that pair. Well, the flow abstraction turned out to be very important for a number of theoretical advances in networking in the 1990s, and 2000s. First and maybe foremost, there was the work by Frank Kelly and later work by Srikant and others on network utility maximization. The notion of a flow was central to that work. In the original Kelly formulation, each source-destination pair, each flow, has a concave utility function, U sub s, that depends on the rate achieved by that flow. And the network-wide problem is to determine the rates in order to maximize network-wide utility. What Kelly's paper showed, among other things, is that iterative TCP-like algorithms with additive increase, multiplicative decrease, and operating at the sender and given feedback like a congestion signal or a pricing signal from along the network path can solve this utility maximization problem. That's a stunning result, a really elegant theoretical justification that an algorithm like TCP, which reflected a tremendous amount of engineering expertise and insight, but was done without a firm theoretical foundation, was shown a decade later through Kelly's work to have some really amazing properties. Kelly's network utility maximization work looked at optimizing flow rates. The combined challenge of optimizing flow rates as well as flow routing was addressed in a really nice paper by one of Jen Rexford and Meng Chang's students. She showed that the iterative optimization of flow paths, routing, with flow rates then iteratively optimized for a given path solves the joint optimization of both routing and rate control at the same time. These two levels of iteration and the fact that they jointly converge to an optimal solution suggest a somewhat natural architectural decomposition of routing at the network layer and rate control at the transport layer, with both of them operating at distinctly different timescales. I'd also note that the flow abstraction was central to the control theoretic analysis of active queuing mechanisms. This was work done by some of my UMass colleagues, and then used again in later work in developing a PI controller similar to what's now been standardized in the DOCSIS standard. In the SIGCOMM community, there's been a good deal of research recently in scheduling jobs and their associated data flows within a data center. Co-flows are defined as a collection of flows between two groups of machines in a data center with associated semantics and a collective objective. Because of this collective objective, flow behavior is correlated, and there's been a good deal of recent research on joint scheduling of co-flows rather than independently scheduling the individual jobs and flows that are components of a co-flow. And as you might expect, there are performance gains to be had by taking this correlation into account when doing the scheduling. And so we've seen that in addition to circuits and packets and content, that flows have been an incredibly important network abstraction. And we've seen some amazing research that's been done built on this abstraction. Now, the final abstraction that I want to talk about is one that's enabled by SDN. And this abstraction is network-wide, it's system-wide, it's enabled by SDN, and it's one in which information about the networking components, their configuration, and their state is all gathered together in one place in a logically centralized SDN controller. The history of software-defined networking is relatively recent. It really just got started about 10 years ago, 2008, with these seminal papers that are shown here. And if you look a little bit earlier, you can see some of the earlier works here that pointed in the direction of SDN. SDN was initially used in wired networks, but more recently has found application in the control plane for 4G and in particular 5G networks, as well as in data center networks. And so clearly SDN is here to stay, as are the abstractions, that of a global network system-wide view that's enabled by SDN. Now, there's been research in protocols for communicating SDN state, OpenFlow, Netconf, and Yang. There's been research in controller architectures for the SDN controller, but really I think the sweet spot for SDN and the abstractions it enables is in configuration management, network management, quality of experience, quality of service. And why is that? Well, with a clear separation between the data plane and the control plane, and a so-called logically centralized approach to managing the network, an SDN controller has a network-wide view of everything that's happening in the network. That is, all of the network state, its configuration parameters, its measurements of performance are all gathered together in just one place. And this provides an opportunity for a more formal approach to intentionally managing the network as a whole. That is, rather than controlling a network component locally at that component with a limited view of what's going on throughout the network, the global network state can be considered. In the SDN view, information is neither hidden nor unavailable, although, as I imagine Tony Efremides will address in his keynote talk, it can be out of date. Before parameters are configured or changed, for example, they can be checked for logical correctness as well as knock-on performance ramifications. The earliest SDN configuration management tools, FlowChecker, Anteater, and HAS, were offline, but subsequent approaches were soon available that allowed for near real-time configuration analysis. NetPlumber, for example, needed only a millisecond to verify an incremental configuration rule change in Google's backbone network. This allows configuration analysis and verification to be automated in real time, with validated changes allowed to be deployed automatically and potentially problematic configurations to be flagged for human intervention by the network operator. This idea of thinking about the network as a whole, being able to abstract and reason about the network as a whole, configure network-wide state, really leads to the notion of programming network state, extending the programming and configuration of individual routers, for example through OpenFlow specifications, to programming the network as a whole. And programming languages are being developed now to do just that. SNAP, which stands for Stateful Network-Wide Abstractions for Packet Processing, is one such language. And while SNAP is about programming network-wide, there's also the capability of programming individual switches. In this case, P4 is such a language. P4 stands for Programming Protocol Independent Packet Processors. And one of the great things you can do in P4 is really program network measurements, for example, at a really fine-grained level of detail, to be able to do things like TCP timestamp options, but to do them in the data plane and at line speeds, as shown in the example here. In this example here, the ingress router has been programmed in P4 to add a header with the delay measurement taken at the first router, 100 nanoseconds in this example. The second router does the same, recording a delay of 200 nanoseconds, as does the final router, which records a delay of 19,740 nanoseconds. Clearly a problem. At the final router or at a later P4 capable router, these delay measurements can be read out. There's clearly a congestion and delay issue end to end. Without measurements, locating the problem and the source of that delay in a network of routers using only end-to-end measurements can be, well, like trying to find a needle in a haystack. With detailed measurements, however, the needle tells you exactly where the problem is, and it does so in real time. Being able to take these fine-grained measurements, being able to report them to a centralized controller like an SDN controller is yet another way to think about correctness, operational correctness. It's a way to detect bugs, it's a way to be able to detect external security violations and also SLA violations. You know, sometimes papers that you read just stick with you for a long time. And I remember reading a paper 30 years ago from folks at Bell Labs when I was working on protocol specification and verification, who had this vision of a self-monitoring and self-checking network. The idea was simple and elegant. You have a network specification and you have observed behaviors. And the question is simply, are they consistent with each other? In that paper, they wrote, an external tester applies or observes a sequence of inputs, for example, messages and packets, to the implementation and verifies that the behavior of the implementation is as described in the specification. Well, that was 30 years ago, and as I recall, they applied it to maybe the alternating bit protocol, but the vision was clear. Well, there was another paper that appeared just late last year, again from folks at Bell Labs, about realizing that vision in an operational network, using software-defined networking, using P4, and using network-wide state abstraction. The paper was about a so-called verification transfers. Performance SLAs, service level agreements, were specified using the extension of temporal logic. Given this specification and these SLAs, runtime P4 monitors were automatically generated to check progressively fine-grained performance measurements against the SLA, for example, from end to end down to individual hops. Using SDN, specific healing actions, rerouting in this case, as I recall, were taken whenever an SLA violation was detected. And I think this paper really showed the real power of network-wide abstractions and logically centralized network-wide views in realizing real-time network management. Well, that pretty much concludes what I wanted to say about how network abstractions have been changing over time, from circuits to packets to flows to content and to systems. And I hope you found it interesting. I hope you found the macro point of view about where networks and research in networks may be heading in the longer term. And I hope maybe it's provided a useful roadmap to you. Well, I've got a couple of minutes left, and I wanted to say a few words about teaching, which I know is something that all of us care about. And actually, believe it or not, it actually ties in also with this notion of abstractions, because after all, we teach abstractions. Well, let me begin by saying just a few words about what it is we teach. I'm not too shy to sort of promote that the 8th edition of our textbook, Computer Networking, Top-Down Approach, is actually out now. And when we took that top-down approach, it was really all about abstractions, because we started from the top of the protocol stack, working our way down, abstracting out what were the functions of the lower layers without actually knowing exactly how they were implemented until we went down to those lower layers. And until we took this top-down approach, networking had typically been taught bottom-up. So it is all about abstractions. Last year at the Open Networking Forum's Connect conference, Nick McEwen gave a really interesting talk about extrapolating forward to 2030. And here's one of his slides, and I don't think people will find it too surprising given the discussion we just had on SDN, making predictions, looking forward. He's saying, well, we'll no longer think in terms of protocols. Instead, we'll think in terms of software. All functions and protocols will have migrated up out of hardware and into software. And point 6 here, routing and congestion control will be programs partitioned across the end-to-end system by a compiler. And we've seen some of that already. Now, number 5 is what I wanted to call your attention to since we're talking about teaching here. And that reads, networking students will learn how to program a network top-down as a distributed computing platform. And we've seen, again, some of that already. But it's the last sentence that I wanted to call your attention to. Protocols will be described in quaint historical terms. And I wanted to use that quote from Nick to ask the question, will protocols indeed become quaint? Will they become just an ancient old artifact? Well, probably not. We're going to need some kinds of protocols to still do some kinds of communication. But as we've seen, routing, plausibly congestion control, and some of the classic protocols are migrating up from protocols and more into a centralized, logically centralized programming environment where they're specified and the results are distributed out to the network routers. So will protocols become quaint? Well, probably not completely, certainly, just as compilers didn't make caches or computer architecture more generally quaint. But I do think that top-down thinking and abstraction will continue to be important. And we do face teaching challenges in terms of what we teach. How do we teach large-scale system concepts like information-centric networking and large-scale systems such as CDNs and data centers? How do we teach the SDN control plane, and how do we teach about programming the network? And then there's a question of who and how we teach. If you look at trends in the United States and other countries in higher education, we see in most countries, especially Asian countries, and in the US and in Europe, a decreasing 18 to 22-year-old population. In the US, the scaling of tuition costs is not sustainable, and because of technology, the technology we work on, it's disruptive, it's constantly evolving, and jobs are going to require lifelong learning. So this notion that our students are 18 to 22-year-olds who come to campus for 4 years, gain knowledge, leave, and then don't come back to campus, I think is going to be changing more towards a notion of university without walls, without boundaries, that our students will be going out for internships, there'll be asynchronous learning on and off campus, and really across a lifetime. And with respect to asynchronous learning on and off campus, we're already seeing a lot of that as a result of teaching during a time of COVID. And I want to wrap up this very quick discussion of networking education, just calling your attention to an ACM SIGCOMM Networking Education Community discussion, August 5th and 6th this summer. And we're looking for white papers associated with that. So not formal papers that are going to be strictly referees, but papers on your thoughts of where networking education is going, both in terms of shared content and what education will look like 5 and 10 years down the road. And you see here the URL where you can get more information about it, and maybe you've seen this advertised on the TCCC and SIGCOMM mailing lists. Well, let me really wrap up here with just one slide of some final reflections. And that's to say that over time, we've seen that the dominant networking abstractions are becoming larger and more encompassing, from circuits to packets to flows to content and finally to systems. These abstractions reflect and influence our research directions and also what we teach and how we teach. I'd say that one major takeaway that I have from a long time working in this field is that there's a diversity of interests. There are many adjacent fields to us, optimization and stochastic processes as always, but now programming languages as well as formal methods, and of course algorithms. And so my advice to students then is, as always, to study broadly. Well, I want to wrap up here just with a word of thanks. I want to thank the conference organizers for the opportunity to present a keynote talk, and I want to thank all of you for your attention and for listening online. If you made it all the way to the end without fast forwarding, you deserve a medal. Later on in the week, as part of the conference, we're going to have a live virtual Q&A. I'm very much looking forward to that and looking forward to talking to all of you in person.